This video is part of a series of videos presenting solutions of problems related to the machine dynamics topic. This video presents the solution of a problem dealing with the specifications of a cam parabolic segment. The problem writes: in a parabolic segment, the lift is 1.5 centimeters and maximum speed is 25 centimeters per second. Find the angle beta, and acceleration. Assume cam's angular velocity is uniform and equal to 5 radian per second. Let's recall first the displacement, velocity, acceleration, and jerk diagrams of a parabolic segment. As the cam's angular velocity is constant, the follower velocity is simply omega times y dash, where y dash is the first derivative of displacement with respect of the angle theta. Also the acceleration is omega times y double dash, where y double dash is the second derivative of y with respect of theta. Finally the jerk is omega times y triple dash, or the third derivative of y with respect theta. In a parabolic segment, of course, the displacement follows a parabolic equation. Thus, the velocity is linear. Here, the velocity is linearly increasing in the first half, and it is linearly decreasing in the second part. Consequently, the acceleration is constant and positive in the first half, and it is constant and negative in the second half. Here there are three discontinuous changes of the acceleration, in the beginning, in the middle and at the end of the segment. Thus, the jerk is infinite in the beginning, in the middle and at the end of the segment. The jerk is zero, elsewhere. In a parabolic segment, the maximum speed is achieved in the middle of the segment, at theta equal to beta over 2, where beta is total length of the segment. The displacement y has a piecewise expression. In the first half, the displacement is given by 2 times L, times, theta over beta, square, where L is the total lift. In the second half, the displacement is equal to, L times, 1 minus 2 times, 1 minus theta over beta, square. Consequently, the first derivative with respect to theta, has a piecewise expression. In the first half, y dash is equal to, 4L theta divided by beta square. And in the second half, y dash is equal to, 4L over beta, times 1 minus theta over beta. The second derivative of y with respect of theta has also a piecewise expression. In the first half, y double dash is equal to 4L, divided by beta square. In the second half, y double dash is equal to, minus 4L divided by beta square. In order to solve this problem, we need first to express V max, the maximum velocity. We recall that, velocity is equal to omega y dash. And y dash is equal to 4L theta divided by beta square, in the first half. And 4L over beta times 1 minus theta over beta, in the second half. It's clear that velocity is maximum for theta equal to beta over 2. To get V max, we substitute theta by beta over 2, in any of the expressions of y dash, and we multiply by omega. Thus V max is equal to 2 times L times omega, divided by beta. Consequently, beta is equal to 2 times L times omega, over V max. Here the lift L is equal to 1.5 centimeters. The cam's angular velocity, omega, is equal to 5 radians per second. And V max is equal to 25 centimeters per second. Substituting L, omega, and V max by their value, and using a calculator, gives beta is equal to 0.6 radians, or 34.4 degrees, considering three significant figures. Y double dash is constant and positive in the first half, and constant and negative in the second half. Y double dash is equal to plus or minus 4L over beta square. Thus the acceleration, or minus the deceleration, is equal to 4L omega divided by beta square. Substituting L, omega, and beta by their numerical values. And using calculator gives 83.3 centimeters per second square. Thus, we have showed here that beta is equal to 0.6 radians or 34.3 degrees. And the acceleration is equal to 83.3 centimeters per second square.